This is part 1 of a tutorial about type classes. In this tutorial, I will talk about type classes from the point of view of type theory and category theory. This will not be about category theory or type theory as such. I'm targeting functional programmers, especially people familiar with Haskell syntax. Scala and other programming languages might benefit as well, as long as they support type classes in some form. And my focus is on understanding the properties of type classes and explaining a certain view that I have found about the general properties of type classes. This will be part of chapter 13 of my book, The Science of Functional Programming. Chapter 13 is the only one that is left unfinished. And part of the reason why it is unfinished is because I found that I don't quite understand type classes, and especially type class derivation. What is the theory behind type class derivation? What are free type class instances? How are they related? So I found that there is an interesting and elegant mathematical way of looking at it, and until I figure out the details, I'm not going to be able to finish properly chapter 13. Once I realized that, I understood that there is actually an interesting theory that I don't think is widely known. So this is, however, quite elementary. So I'm going to target functional programmers, and I'm not going to be very academic in my tutorial. The plan is that I will first look from a more practical point of view at the signatures of type classes. And I find that if you combine all type class methods into a single type signature, then type classes can be algebraic with type signatures of this sort, co-algebraic with type signatures of this sort, or neither algebraic nor co-algebraic. I will explain what that means and how that works. But this is the first step. So once you understand that, you see that the properties of these type classes, like monoid, functor, monad, and applicative, are quite different from the properties of the other type classes that I called co-algebraic, such as show or traversable. And in fact, their derivation patterns are different. The next step is to discover what are those derivation patterns. So how can you derive new type class instances from previous ones? And I find that there are some universal patterns, but those patterns are different for these type classes, for algebraic ones and for co-algebraic ones. So the next step is just to discover more or less heuristically what those patterns are. Then it turns out one needs to go a little more into category theory and use some very simple definitions from category theory, namely morphisms and functor algebras and monad algebras. So I'm going to go slowly through this. Category theory here only provides definitions and language, so such as monad algebra. This is a definition. This is easily translated into the programming language as just a specific kind of design pattern or type signature. And so no real knowledge of category theory is used here, just the language, the definitions and words. This is convenient, but we do not actually use any theorems of category theory here. So no real knowledge of category theory is necessary, just the language that is convenient. Then I will show that we can express type class laws as either monad or comonad algebra laws. So these laws are equations which for each type class are different, but it turns out that you can define a certain monad or a certain comonad, and then all the laws will be coming from a single universal equation. And using that, we can actually prove that the universal derivation patterns that we discovered here heuristically are valid, that they also conserve the laws. In other words, if you begin with types that have a type class evidence that satisfies the laws, and you derive new type class instance, then that new instance will automatically satisfy the laws. There is no need to prove that the laws are satisfied. So this is the plan. So the usefulness of this theory is in showing that there are type class derivation patterns that automatically satisfy type class laws. That is, I believe, the real usefulness from the point of view of a functional programmer. Let me show a summary of what that knowledge is. So I'm not going to prove yet what it is, so I'm just going to show the results. And I'm using Haskell syntax to describe type classes. So here's this Haskell syntax to define a type class. And imagine that we define a type class like this, where P is a type constructor, which is a covariant functor. Or we define like this, the type class. So just a single method with this type signature. I will explain why this is interesting to define it like this. It is interesting because many type classes are equivalent to a definition of this kind or a definition of this kind. Although it's not convenient, of course, in practice to use this sort of definition. Now, if you have a type class of this sort, then the unit type is always an instance. And if you have a type class of this sort, then the void type is always an instance. And then there are derivation patterns that are like this. So if A and B are types that belong to the type class C, then the pair of AB, or the product type in the language of type theory, is also an instance. And if you have a type class like this, then the either of AB, or in the language of type theory, the coproduct type, is also an instance. So that is the first pair of type class derivation patterns. And this works for any type class of this sort or of this sort. This next one is that if A is an instance, or has an instance, then the function type R to A, where R is any fixed type, doesn't necessarily have to be an instance, have to have an instance, then this function type has an instance of the type class C. And for the coalgebraic types, it's the pair RA, where R does not necessarily have an instance, but A does. Then this pair is an instance. Now, compared with this one, where both needed to have an instance, and without that it doesn't work. And here it's not necessary, only one really needs to have an instance. The next pattern is the recursive type. So recursive types are defined in type theory using fixed point of functors. So fixed points, either least fixed points or greatest fixed points or some other fixed points, are always going to have an instance as long as the functor f has this property that it preserves the type class. So if any type x has an instance of the type class C, then fx also should have an instance. So if this is satisfied, then the fixed point of f will have an instance. Finally, there are free, so-called, and co-free, so-called, instances. So, in other words, if T is any type whatsoever, then there's a type constructor that always creates an instance of this type class, and then that is called free, instance of that type class. You probably know about free monad or free functor or free monoid and so on. So these are type constructors that create instances from any type. And similarly for coalgebraic type classes, they're co-free instances, and they're different. So algebraic type classes do not have co-free instances, and co-algebraic ones do not have free instances. And also here, unlike all these patterns where the patterns work generally for any type class, and they can be implemented generically for any functor P and any functor F. These ones are not generic, so they have to be implemented specially for each type class separately. And it is not trivial to find them. So we, for example, we know that there is an applicative functor type class and there is a free applicative functor. In order to find that, there were several research papers with proofs showing that they have correctly found it. It's not trivial, it's not obvious to find that. So that is the result of having this theory, and the new instances are automatically lawful. So if, for example, we have here the type class C, let's say, is a monad type class, then if you have two monads that satisfy the laws, then the pair of two monads, so a pair of MA, NA, so let's say MN are two monads, then MA is the monad applied to the type A. Not to be confused here, because this A and B, there are types here, but actually sometimes we have type constructors instead of types, and so it's the same theory at the level of type constructors. So then the pair of two monads is again a monad, and it again satisfies the laws. And it doesn't have to be proved, because we have a proof that works generically for all type classes. That is the good result of this theory, that we can prove these things once and for all, that these patterns work and preserve the laws as well as the type class instances. And so programmers are free to use those type class derivations without having to check the laws every time. That is the advantage of having this theory. Now, certainly I would like to note that programmers who use this stuff don't need to go through the proofs. They don't need to learn about the techniques of how functor algebras and monad algebras are defined and how you prove their properties. The proofs exist and they can be checked, and I will write them out, at least in the book. I will show some of these proofs in the tutorial as well. But the programmers do not need to go through the proofs, do not need to know the definitions. These are the applications. The programmers need to know these types, need to know what is the correct type of free or co-free of their type class, and that's enough. So let me begin from our first step, where I showed, well, why can we write type classes in this way or in this way? Because that's not the usual way that type classes are defined. So here's an example of a monoid type class. So it's defined like this. So you have two methods. One method has this type signature, another method has this type signature. So the trick that we use is that we gather all type class methods into a single type signature. So we use currying and uncurrying as necessary in order to achieve that. And this gives us an equivalent type, which is going to be of a simpler form. So here is what we do for the monoid. We curry this, so the type of M append becomes TT to T. Then we replace the type of M empty by this unit type to T, which is a function, but it's equivalent as type. It's certainly not equivalent at runtime in terms of its performance and so on, but as type it is equivalent. So then we have two functions of types something to t, and that is equivalent to the co-product of their arguments going to t. So that is equivalent to this, maybe pair tt to t. So this one function with this type is equivalent to the two functions written here. So in this way, we have simplified the signature, and now the signature has this form, pt to t, where p is a type constructor that we just define for this case like that. So if we define p like this, and we know this is going to be covariant, a covariant functor, then we have replaced the type signature of the monoid by an equivalent type signature of the form pt to t, and that is called algebraic. So why is it called algebraic? It's because in category theory there are definitions of a functor algebra. So if P is a functor, or covariant functor, as we say, then P functor algebra translated into types is a type T and a function of type pt to t. So that is all that is translated into types. So I'm not going to talk about how this works in category theory in the abstract. I'm only going to talk about types. So for the programmer, a P functor algebra is just a type T. So there can be many P functor algebras. Each one of them is a certain type T and a certain function of type pt to t. So you can have different types, or you can have even the same type with different functions, and those are different algebras, different P functor algebras. Now, in category theory, sometimes this is called a P algebra or a F algebra or something like this, and this terminology is insufficient for the purposes of type classes, because we will later have monad algebras and the letter needs to be different. So we need to specify very clearly what functor we're using, or are we using a monad, or are we just using a plain functor. Also in category theory, there's something called a P functor coalgebra, or a functor coalgebra, or a P or F coalgebra, or something like that. But I will be always saying P functor coalgebra for clarity. And that's a type T and a function of type T to PT. That's just how it is defined. And so the functions of these types, PT to T or T to PT, they're called structure maps in category theory. So in category theory, it is a structure map. We're going to say that this is just a function of a certain type, and we have transformed equivalently the type signature of a type class into a single type signature of a structure map. So we say this is the structure map of this type class. And we can do that in certain cases, for some type classes. And if we can do that, and we find that the form is pt to t, then the result is that this type class is algebraic. Let me step back a little and say what is a covariant functor. Now I want to make a very short digression and clarification. In the entire presentation here, we need covariant functors. So P and F here, for example, they are covariant functors. And here, P is a covariant functor. So what does it mean that it's covariant? It means that it has an F map. It's a type constructor, and it has an F map method that satisfies the laws of F map of a functor, which is identity law, that F map of identity function is again identity function. The type signature of F map is standard. I'm not going to write it out. and it must also satisfy the composition law, that the composition of two f maps is equal to f map of the composition of the functions. So if a type constructor has such a method, then we call it a covariant functor. Sometimes, however, people learn about covariance from object-oriented programming and subtyping. And I would like to stress that this is not essential. Covariance is not defined always through subtyping. We can talk about covariance in just in relation to a specific type constructor with no subtyping at all necessary to be mentioned. We can have a language that does not have subtyping where we define f map and it satisfies the laws and we have a covariant functor. So covariance is understood in category theory and translated into type theory, translated then into the programming language, is just this definition that we have an f map with its laws. It has nothing to do necessarily with subtyping. Now, if you have a language with subtyping, then a covariant functor will have a certain subtyping property. But that property follows from the fact that it is covariant. It cannot be used as a definition that it is covariant. So the structure of the functor itself must be such that it allows the fmap method. And if that structure is correct, then it is covariant. Subtyping is secondary to that. And we are not going to talk about subtyping in this tutorial because it is not relevant. And so I just want you to be clear that I'm not talking about covariant functors in relation to subtyping or defining covariance through subtyping. That is confusing and incorrect. Covariance is a property of a functor itself, of a type constructor itself. It can be covariant or not, or contravariant, with no regard for any subtyping that is in the language. So then, let me go to another example, the functor type class itself. Now, the functor type class is defined like this. It has a function fmap. We do not write the laws in Haskell. It is not essential at this point. How can we see if this type signature doesn't look like of the type pf to f or f to pf or anything like this? It's more complicated. But what we need to do is we need to transform this type signature into an equivalent type. And also, because this type class applies to type constructors and not just to types, we need to change the type signature a bit. So whereas the usual type signature for algebra is pt to t, where t is a type constructor, this cannot be a function. We need to apply the type constructors to something, so to some arbitrary type x, say. So instead of pt to t, we need to write something like ptx to tx. And so here f is the type constructor that we're looking at, so we need to write something like pfb to fb, like I was writing here, where b is a type parameter, so b is an arbitrary type. So that is what we have to do. And in order to transform the type signature of fmap into the form of this sort, we query the type, so we get this a to b and fa going to fb. And now you see this is fb, so we can rewrite it in this form if p is defined like this. So p is a higher-kinded type constructor that takes a type constructor f and returns another type constructor, which applied to x gives you this type. And that is fine. So that is covariant in f, and that's good enough. So But note, however, that the parameter a here only appears at the right-hand side, but not on the left-hand side, which means that it is used existentially. So when we construct a value of this type, we need to specify what that a is, but once we have specified it and constructed the value, it is getting hidden and we do not see what that a is. So that is how existential types work. And so we see, therefore, that the type constructor f is algebraic. Not the type, the functor type class is algebraic. However, the functor type class is also co-algebraic because we can transform this type signature in a different way into a type signature of this sort. And then we see this is in the form fa to pfa, where p is defined like this, where again the parameter p is used existentially, and the type parameter x is actually in a covariant position. So this is still a covariant functor. So if f is a covariant functor, then pf also is a covariant functor. And so, in fact, the functor type class is both algebraic and co-algebraic at the same time. And as I was already saying, here the co-algebras and algebras are understood at the level of type constructors. So it is a type constructor f and a higher kind of type constructor p, so that we have not a function of type pt to t, but we have a function of this type for all x, pfx to fx. So that is the form into which we were trying to massage our type signatures in order to discover whether a given type class is algebraic or co-algebraic.